Let us take a look at this DFA. The language of this DFA is just a set containing one string, 1. Here is another DFA whose language is a set containing two strings, 1, 1, 1. You can observe that the path that leads to the acceptance does not have a pump, meaning none of the symbols are being pumped repeatedly with a self loop or a longer loop. Such DFAs which do not pump any symbol in the path of acceptance lead to languages with finite number of strings. We already declared that a language containing finite set of strings is a regular language. You can always create a DFA with finite states that can accept every string in this finite language. The trouble starts when we deal with languages that contain infinite strings with unbounded length. You have seen them already. Few are regular and the rest of them are non-regular. How do we identify which of these languages with infinite strings is regular and which one is non-regular? That's where the concept of pumping length comes to our rescue. For a DFA to accept a string of arbitrary non-bounded length, definitely it has to have a pump for few of its symbols. Take this DFA example, which has 3 states. This DFA accepts a string 000111, which has 6 characters. Notice that the number of states are lesser than the number of characters in the string. Common sense tells us that few of these states have to repeat for sure if the string were to be accepted. It is this property we are interested in about a DFA, this pumping property. You will see shortly the formal notation that we will be using in Pumping Lemma. I'm giving you a glimpse of it right here. So we can break down any string accepted by this DFA into the format x y to the power I z. X and z can be empty strings or strings of finite length. Y cannot be an empty string. The minimum length of y is 1. Let me show you different combinations in which I can split 000111 for this DFA. If I consider the pump with the symbol 0, I can split the string as x is equal to empty string, y is equal to 0, where I is equal to 3, and z equals to 111. If I consider the pump with the symbol 1, I can split the string as x is equal to 0001, y is 1, and then I would be 2, and z would be e. Here is a DFA where we have a loop across several states. Okay, so the strings that are being pumped in here are 110 as well as 1010. For a generic DFA, the XYZ breakdown can be visualized this way. X and Z could be empty string, which is epsilon, meaning they can be completely absent. What cannot be epsilon is Y. Okay, so Y is the string that is pumped and the length of Y should be at least 1. Given this knowledge about pumping that happens in the DFA, let me make a more formal argument regarding the DFAs that accept strings that are pretty large when compared to the number of states they have. Take a string of length p. For a start, let us assume p is n, which is the number of states in the DFA. Let's say the DFA accepts the string of length p. We shall look into the state transitions that lead to the acceptance of the given string. For a symbol S1, the DFA transitions from Q1 to Q2. So after reading one symbol, the DFA traversed 2 states. So after reading the second symbol S2, the DFA transitions 3 states. Hence, after reading the full string, with the length p equals to n, the DFA would have traversed n plus 1 states. But there are only n states in the DFA. Hence, one of the states should have repeated itself in this chain of transitions. Hope this makes sense. If there are n unique states in DFA and we have n plus 1 states traversed, common sense tells us that one of the states would have repeated. The repetition of a state indicates that there is a pump. When there is a pump, it means we encountered both x and y in this string. Hence, we can say that the length of x and y put together is less than or equal to p, because the length of x and y is definitely less than p plus 1. Putting it all together, here are the three properties of a large string accepted by a DFA. It can be broken down into this format x, y to the power I, z, where x and z can be empty strings. Y cannot be an empty string, so its length is greater than 0. And finally, the length of xy should be less than or equal to p. These three properties have to be true for any large string in the language accepted by the DFA. Alright, here is the interesting part about pumping lemma. The three conditions will be true for all strings accepted by the DFA. So to prove a language to be non-regular, we first assume that it to be a regular language. So if the language is non-regular, then it is likely that some of the strings will not satisfy all the three conditions of pumping lemma. That is where we arrive at a contradiction and confidently say the language contains a string which does not satisfy the three conditions together, hence it is a non-regular language. But finding that one string that does not satisfy all the three conditions is where new learners like you spend countless hours. While I empathize with this process, I must admit that it gives you a lot of satisfaction if you find the string that does not satisfy the three conditions together. Let us get started with this example. You have seen this before. According to this language description, the string 0 to the power p, 1 to the power p is in the language. Let us break down this string into xyz format, as xy is less than or equal to p. The length of xy is less than or equal to p. The string xy will only contain zeros, clearly. Hence, y should contain only a 0 or a bunch of zeros. So the DFA should be pumping those zeros indefinitely, and the general format of the strings that are accepted would look like this: x, y to the power I, z, where I can take any values from 0 to infinity. So x, y, y, z is part of the language, but that causes imbalance of number of zeros and ones in the string. X, y, y, z will have more zeros than ones, hence a contradiction. The strings of the given language do not accept all the three properties of pumping lemma, hence this language is non-regular. I'm going to show you one more example. In this language, the number of zeros and ones should be the same, but their order does not matter. But to prove this language is non-regular, we just need that one string for which we need to prove a contradiction. Clearly, 0 to the power p, 1 to the power p belongs to this language, and we can repeat the same steps as the previous example to prove that this language is non-regular. While the pumping lemma can be used to prove a language is non-regular by finding that one string that does not satisfy all the three properties, you have to understand that just by showing One string from the language that satisfies all the three properties does not prove it to be a regular language. Pumping lemma is used to proving languages are non-regular. It cannot be used for proving languages to be regular. If you have to do that, you have to check these three properties hold true for the infinite strings in that language, which is not possible computationally. I understand I threw a lot of concepts at you in this short span of time. This particular topic makes a lot of sense if you read through the textbook section after watching this video and then come back again to watch it. Hopefully, by then, you should be good with the concept of pumping lemma. If you have any pressing questions, please feel free to reach out to me. Okay? See you in class.